All right, so today we're going to just continue what we were doing yesterday, Friday, as far as solving trigonometric equations. All right. However, today we're going to be solving ones that we'll need assistance from our calculator for. All right, like we won't just always be able to go straight to our unit circle. All right, so we'll start off very similar to some of the stuff that we did Friday.
We did one of these on Delta. We had one where we had to do like cosine.
You had to do your inverse.
-1.
Yeah. All right, guys. So here, all right, we have two separate trig functions. So we're going to have to replace one. All right. Obviously, we always replace the one that's squared, and we're always going to be using our Pythagorean identity. So in this case, we have 1 plus tan squared x is equal to secant squared x. All right, so wherever I see a secant squared x, I'm allowed to replace it with 1 plus tan squared x. So I will do that here. Everything else stays the same, of course. I am going to bring this 4 over to the other side, so subtract 4 from both sides. Remember, this thing is eventually going to look like a quadratic, and to solve quadratics, we always want them set equal to 0. Okay, so of course now I can combine these like terms, right? I have 1 and minus 4. All right, so I just have my 1 tan squared x term. I just have my 1 tan x term. All right, and then I have 1 minus 4, which is negative 3. So if you want to think of this in terms of u's, right, to make it look simpler, remember you don't have to do that, but you can. All right, this would look like u squared minus 2u minus 3. All right, so this would factor to u minus 3 and u plus 1. All right, so of course here this is the same thing, but just with tan x's instead of u's, right? So this becomes tan x minus 3 and tan x plus 1. Of course, when we have two factors equal to 0, we set each factor equal to 0 and solve. So here I would just add 3 to both sides to get tangent of x is equal to 3. And here I will get tangent of x is equal to negative 1. All right, now this tan of x equal to negative 1 can be done just from our unit circle values, okay? And here it doesn't really tell us, whether it wants us to solve it in radians or degrees. All right, usually you'll be told. All right, if it doesn't tell you, either would be fine. All right, I typically do radians more, but for this case, I'm going to actually do degrees. All right, so if we look at our unit circle and say, okay, where is tangent of x going to be negative 1? All right, on our unit circle, all right, that's going to happen at 3 pi over 4 and 7 pi over 4. Oh, of course, I said I was going to do this in degrees, so I should probably do it in degrees. So that's going to be 135 degrees. And 7 pi over 4 would be 315 degrees. Okay, now tangent of x equals 3, all right, is where we're going to have some trouble here. Okay, so part of it's going to be relatively easy, all right, but it also depends very specifically on whether we're trying to find all solutions or whether we're just trying to find solutions between 0 and 360. Okay, So we'll say for now, we'll say that our solutions, we want to be between 0 and 360 degrees. Okay, of course, including 0, not including 360. All right, so I'm going to come up here to my trusty handy-dandy calculator. All right. Remember to solve for x here. How do we break apart a tangent and an x? Inverse, right? So if I take the inverse tangent of both sides, this is just going to be tangent, x equals inverse tangent of 3. Right, we do want to make sure that we are in degree mode. I am. All right, so we can say inverse tangent of 3. Right, and this gives me 71.565. We'll say 71.6 degrees. All right, however, all right, we have to remember that inverse tangent only gives us solutions between negative 90 degrees and positive 90 degrees. Okay, so there's going to be somewhere else on the other side of the unit circle, all right, where this would be a solution as well. Okay, so we kind of have to be careful here. So 71.6 is somewhere up here, right? So this is my x. Who remembers what the period of tangent of x is? Oh, well, that's the range. I'm talking about the period. How often before it repeats itself? It's just pi. Sine and cosine are 2 pi. Tangent is 1 pi. Of course, that's not counting any extra b being added in, right? Remember when we were graphing sine and cosine, we found period by doing 2 pi divided by b. Right? If you want to do tangent, it's actually going to be pi divided by b, right? But in this case, the b is just 1, right? So our period is just pi. Now, what is pi in degrees? Right? Pi is in radians, so if we switch that to degrees, what is it? 180 degrees, right? So I can actually add 180 degrees to this, right? And that would put me down here, right? Where remember in the third quadrant, tangent is also positive, right? So if I add 180, I would get 251.6.
Why are we adding
Because remember, with the way the unit circle works, right, there's really always 2 places on the unit circle that's going to give us the solution that we want. All right, but when we do inverse tangent, remember when we first started talking about inverse tangent, well, inverse trig functions in general, we had to restrict the domain of the function so that it would pass the horizontal line test and so that it would have an inverse function. Well, that kind of messes us up a little bit. It only gives us a little window that it's looking at. All right, so for tangent, tangent's actually the easy one, right? You're always just kind of going to be adding 180. And we'll get to some more difficult ones in a minute, right? But so, and just for example, right, if we say, oh, okay, well, what is tangent of 71.6? Right, well, we should know it's 3, right? Of course, we round it a little bit, so there's minimal rounding error there, right? Well, we say, okay, well, what is tangent, all right, of 251.6? It had better be, right? So we said here, oh, we wanted tangent of x to equal 3. Oh, okay, well, tangent of 71.6 equals 3, and tangent of 251.6 equals 3. Okay, so that's, we can always test ourselves kind of to make sure that we got the extra other solution. Does that make sense? Okay. All right. Go ahead and try this one. It will work similarly. Of course, do remember that you're going to want to set it equal to 0 first before you can factor. Okay, so let's take a look here. All right, so we have, 4 tan squared x plus 5 tan x minus 6 is equal to 0. All right, so now our a is something other than 1. So when I factor, I'm going to do my trash can method here. So a times c is negative 24, and b is 5. All right. So this looks like it should be 8 and negative 3. All right, 8 times 3 is negative 24, and 8 plus negative 3 is 5. All right, so I'm going to have 4 tan x plus 8 and 4 tan x minus 3. Of course, this is where I have to take out the trash, right, to factor out any extra stuff from each factor and throw it away. With this first factor, I can pull out a 4, and I'm left with tan x plus 2. Right here, I can't pull out anything, so it stays 4 tan x minus 3. Of course, I throw away what I factored out. This is now my factorization. All right, so I say, all right, set each of these equal to 0 and solve. So this piece will give me tangent of x is equal to negative 2. All right, here I would add 3, divide by 4. So tangent of x is equal to 3/4. Right, now, neither of these values are on my unit circle. All right, so we're going to have to use our calculator for both. All right, so first I will do the inverse tangent of negative 2. All right, now this gives me negative 63.4. Right, all right, so this is not between 0 and 360. All right, now again, we said for tangent, as long as there's no multiplier here with my variable, which there's not, right? What is my period for tangent again? Pi, or 180 degrees, all right? So I can simply add 180 to this, right? And that's going to give me 116.4. Sound about right? No, I'm sorry, 0.6. All right, so that's one of them. All right, now, do be mindful. Remember, our inverse will only give us stuff over here. All right, 116.6 is over here somewhere. All right, now, the negative 63, if we think about it in the negative direction, it's down here somewhere. All right, so I added the 180 to get a positive value here. I can add 180 again. Remember, if I add 360 to this, that gives me a coterminal angle. It just gives me a positive one, right? So if I add 180 again, all right, that will be 296.6, which of course would be right here again, right? Just now it's positive, and it's between 0 and 360, which is what we want. All right, so these would be my two solutions here. Again, you can always test yourself, right? Like, what is tangent of 116.6? It had certainly better be close to negative 2 here. We rounded, so it'll be a little bit off, but that's pretty darn close, right? And then, of course, you could test yourself with this as well. So 296.6. Yeah, right? So we're good. We are confident that both of these will give us the negative 2 that we want. Okay. So now we can do the same thing over here. All right. Now I'm going to do the inverse tangent of 3/4. All right, and we get 36.9 degrees. And that's a good one. We like it, right? It's between 0 and 360. We're good. Of course, the period of tangent is 180 degrees. So if I add 180 to this, all right, I will get 216.9. Yes, no, maybe so.
Sure.
All right. Again, you can always check yourself, right? Now we're trying to get 3/4, so close to 0.75, right? So if I do tangent of 36.9, I get 0.750, right? If I do tangent of 216.9, right, I also get a 0.750, which is 3/4. So we're good here. Questions or concerns there? Okay. Okay. So now it says to approximate the solutions between of x equals sine x in the interval. Okay, so now when we have stuff like this where we have a regular x and an x in our trigonometric expression, all right, there's really no way to do this algebraically, not even how we were, using our inverse tangents and stuff in the last problem, all right? So what we're going to have to do here is do it solely by graphing. All right, now it does say between negative pi and pi. So now I'm going to put this in radian mode because we're clearly dealing with radians. All right. It says my window here should be between negative pi and pi. So my x min is negative pi. All right. My x max is positive pi. Scale of 1 should suffice here. All right. Now, sine of x, we know goes from negative 1 to positive 1. So we want to see that. I'll just go from negative 2 to 2 here with a scale of 1. All right. So now in my y equals, I'm going to put in y1, I'm going to put whatever's on the left-hand side of my equal sign. In this case, just x. All right, in y2, I'm going to put what's on the right-hand side of my equal sign. So in this case, sine of x. All right, I've already set up my window, so when I graph this, it should give me some nice stuff going on here. All right. So how do we know where these two things are equal to each other? Where they intersect, absolutely. So we can use our calculator here. We hit second trace. Guys, I can't specify enough. Do not just hit trace and try to figure out where this is. Okay. I know students do that all the time because they're way off, right? Your calculator is very precise and has a very small margin of error, right? So when your calculator does these things, even though it does use an estimation technique, mainly Newton's method primarily, but it estimates it to such a precise exact that you're not I can tell when somebody just uses the trace feature because they're so far off, right? The calculator, when you do the actual second trace and you come down here to intersect, right, it will be very, very exact. Right? It looks like it's right here, so we can just do this. And yes, the intersection is 0, 0. So that should actually kind of make sense, right? Because we know sine of 0 is 0, and of course, when you plug 0 in for x, you get 0, right? So here we know that x is equal to 0. And that's it. There really is no other way of doing it. All right, now this one you could have because you could reason your way through it, right? Oh, well, sine of 0 is 0, and of course you would get 0 here. But in general, something like this, you're just going to have to use that intersection feature. All right, try this one. So you'll have to use your calculator, and you will just simply find the intersection. Yeah, well, when it says from negative pi to pi, right, if it wanted it in degrees, it would say from negative 180 degrees to 180 degrees. So in this case, we would definitely want radians.
So for the interval, we're just doing it for x and max and x max.
Well, yeah, our x min would be negative pi, our x max would be pi. Yep, absolutely. Now your y min and max, you just kind of have to figure that out, right? Well, we know cosine typically goes from negative 1 to 1, right? But when you multiply it by 4, that changes the amplitude, right? So now my amplitude is going to be going from negative 4 to 4. So, and you want to be able to see all of that, right? So I just kind of go an extra usually. Like I would go from negative 5 to 5 with your y's. Okay, so because the calculator does all of this, it doesn't take too terribly long here, right? So we can go to y equals. We have 4 cosine x. And down here we just have x, all right? We are going to want to mess with our window a little bit. Of course, negative pi to pi stays the same. And here, because of our amplitude being 4, I'm going to go from negative 5 to 5 so we can be sure to see the whole thing. All right, so now when I graph, whoa, what is going on here? What'd I do? Oh, 2 x's. That's interesting. All right, so we obviously have 2 points of intersection here, so we're going to have 2 solutions, so we need to find them both. All right, so we come to intersect. I always go from left to right, so come down here, enter, enter, enter. All right. Yeah, the phone calculator is the estimation is very, like much more poor than the calculator. If your graph looks like a flat line, do both of them look kind of like flat lines? That's because you're in degree mode. Put it in radian mode. Right, just making sure that I knew what you were doing. Obviously. Yeah. Well, your window is just different than mine. Right. So go to your window. Right. And go, your x min should be negative pi. And your x max should be positive pi. And then your y min should be negative 5. And your y max should be positive 5. No, it totally depends on how high and low your sine curve goes, right? Because it was 4 cosine of x, that means our amplitude was 4. And since our baseline was still 0, like it wasn't shifted up or down, then we know from 0, up 4 is 4, down 4 is negative 4. I did just an extra one so that I'd be sure to see the whole thing. Like instead of going from negative 4 to 4, I went negative 5 to 5, just so I'd be sure to see it all.
whenever we click second trace and then the intersect, it
Uh-huh.
don't do it for me.
What do you mean?
Like,
I mean, you still have to go like move the cursor over afterwards and hit enter 3 times.
like
Right.
if I go like second trace and go down the
Intersect. Yep.
I have to
Okay, now move it over to where it looks like they intersect, and then hit enter. Enter again. Probably enter again if it's like ours. Yeah. So negative 2.1. I mean, it's close, right? It's slightly off, but it's pretty close. The calculator one isn't near as, I mean, the phone app isn't near as accurate as the one like on your computer. All right, so negative 2.133.
second trace.
All right, so then second trace, we go down to intersect again.
Go down to
All right, then we use our arrows to get our cursor over to the second point of intersection. Hit enter 3 times. What's that? No. 1.252. Guys, if you're ever having problems with the calculator on your tablet or on your phone, Desmos will do this no problem. So you can always just hit up desmos.com. Like it'll do any of this stuff that you.
like on a test, like if we use our phone and we're close.
Typically, because I've noticed that the phone is
The one
slightly off. If you're really close, I typically give it to you.
The one on the computer doesn't work at
No, that's so weird. Because some people say it works fine at the house, and some people say it doesn't.
I work at school, but like whenever I get in my house, it doesn't work.
See, I would go to the help desk and ask them what.
Like the school stupid that they lock it so that you only use the program when you log the school on time.
That's completely stupid.
Yeah.
Like you're not just only using that calculator at school. That's the dumbest thing I've ever heard.
Like it comes up and it says error, you can't go to this site.
I got you. It's probably some legality thing, would be my guess, because it can't really be legal to just steal TI-84 free. You know what I mean? So there's probably some legal issue where they're allowed to use it while in school, but then they don't want you to be able to outside of school, so that they force you to buy one. Basically, that would be my guess. Probably not. But the school, they probably let the school do it because the school buys class sets for every class, right? So they just assume that you've already bought hundreds of these things, which we have, right? So they're like, you can just use the software while you're at school, probably as part of COVID stuff also, right? Okay. Are we okay with how to, graph these and find intersections? Okay. All right, so now find all solutions of the equation tan squared x equals 1 without using a calculator. So this is okay. This is not a big deal. This is more like the stuff we were doing on Friday. All right, so we go ahead and, of course, to undo a square, we take a square root. All right, so this will just give me tan x, which is what I want. All right, do be mindful that when you take the square root of a number, it's plus or minus, right? So this is plus or minus 1. All right, well, tangent is positive 1 at pi over 4, and tangent is negative 1 at 3 pi over 4. Now, of course, tangent is also positive 1 at 5 pi over 4 and is also negative 1 at 7 pi over 4. But since it says to find all solutions, really you can just take this and say, okay, plus n pi. Because we know that the period of tangent is pi. So if we just add n pi to each of our solutions, this will actually also go ahead and cover the other one on the unit circle, right? 5 pi over 4. And this one will cover the other one on the unit circle, 7 pi over 4. Now, I'm not picky about it, right? If you said x equals pi over 4 plus n pi, and 5 pi over 4 plus n pi, and you're naming all of the solutions twice, but I don't care. You're naming all of the solutions. That's fine, right? So I wouldn't be picky about that, but you can kind of limit your writing just by doing this. Any questions or concerns there? Okay. And just for like delta math purposes, if we were doing this in degrees, right? Well, pi over 4, right, is 45 degrees. So you could also say plus 180 n degrees, right? That's pi and 180 are the same thing, right? So, and here you could say 3 pi over 4 is 135 degrees. So then you could do the same thing here. All right. Typically, I'll ask you much more often in radians. All right, but delta math I think does both, right? So just so that you're aware of how to do both. It's really the same concept. It's just which mode are we in? Okay. Solve sine squared of 3x minus 2 sine of 3x plus 1 equals 0 for x between 0 and 2 pi without using a calculator. All right, so go ahead and, we'll have to factor this, set each factor equal to 0. All right. So we'll go ahead and do this one together since we're not allowed to use a calculator, and we're probably just going to have to stop somewhere where you wouldn't think you would have to stop. Remember, when we have some other number, some b, all right, we don't worry about it until the very end. Okay, don't try to do some magical math that gets rid of it. You can't. Okay. So here, all right, this should be able to factor to let's see, -1 and -1. So this would be sine of 3x minus 1 and sine of 3x minus 1. All right, now you really don't need to write it both, right? You don't need to find the solution for both of these because they're going to be the same. You could also just think of this as, not that you couldn't write it exactly like I just did, right? But anything times itself is just that thing squared. All right, so now all we have to do is take the inside, set it equal to 0, and solve. Right, so we're going to get, okay, there we go. All right, so we'll have sine of 3x. We add 1 to both sides, so that's equal to 1. Remember, we don't do anything with this 3 at all. All right, all we have to do is say, okay, let's pretend like this is a normal x. Where is sine 1? All right, well, sine is 1, all right, at pi over 2. All right, but now we're not saying x equals 3 pi over 2. We're saying 3x is equal to pi over 2. All right, well, now that we don't have this 3x attached with this sign, all right, now we can go ahead and divide by 3, which is the same as multiplying by 1/3. All right, so x is going to equal to pi over 6. All right, now, again, just like on Friday, it's tempting to stop right here, all right? But we have to realize that our period is going to be changing, all right, because of that 3 in front of the x. That's my b. So my period is 2 pi over 3, which, to get a common denominator, is 4 pi over 6. Now, that's how often my solutions are going to repeat themselves, right? So every time I add 4 pi over 6 to my original solution, I'm going to get another solution. So what is pi over 6 plus 4 pi over 6? 5 pi over 6. All right, what's 5 pi over 6 plus 4 pi over 6? 9 pi over 6. What happens if I try to do it again? Yeah, it's too big, right? If I add 4 pi over 6 to 9 pi over 6, I get 13 pi over 6. 13 over 6 is bigger than 2. Remember, I'm just trying to stay between 0 and 2 pi here. Okay, so these are going to be all of my solutions. Fair enough? All right, try this one. Okay, so this has a leading coefficient other than 1. So I'm going to use my trash can method here. So 6 times negative 2 is negative 12 and negative 1. All right, so this is going to be negative 4 and 3. So I'm going to get son of a biscuit. All right, so 6 cosine of x minus 4 and 6 cosine of x plus 3. All right, this was the trash can method, and my a was something other than 1, so I need to take out the trash. All right, here, 6 and 4, I can pull out a 2, and I'm left with 3 cosine x minus 2. Here, with 6 and 3, I can pull out a 3, and I've got 2 cosine x plus 1. Of course, whatever I pulled out is trash. We just throw it away. All right, so here is our factorization. So I set each factor equal to 0 and solve. So here I'm going to add 2, divide by 3. So cosine of x is equal to 2/3. Here I'm going to subtract 1, divide by 2. So cosine of x is equal to negative 1/2. All right, this one we can just do using our unit circle. All right, so cosine is negative 1/2 at 2 pi over 3. All right, and at 4 pi over 3. Over here, however, we're going to have to use our calculator. All right, so we are in radian mode, so I'm good here. All right, so I can do inverse cosine of 2/3. All right, and that's going to be 0.841. All right, now let's kind of try to think about this. All right, so all right, so 0.841. Remember, this is 0. This is pi over 2, which is roughly 1.57. This is pi, so 3.14. Right. This is 3 pi over 2, so that's 4.71. And we're back here at 2 pi, which is 6.28. All right, so 0.841 is somewhere over here. All right, so that's 0.841. All right, what other quadrant, because this is a positive value here, right? What other quadrant is cosine positive in? 4. All right, so I have to find some other angle here down in the 4th quadrant. It's going to have the same reference angle. All right, so here we're just going this direction, which is negative 0.841. All right, so let me do that a little bit better so that we can all see it. So this would be negative 0.841. Okay, but I don't want negatives, right? I want it between 0 and 2 pi. How can I get a positive angle that is in the exact same location as this one? Yeah, just add 360. Well, in this case, we're adding 2 pi, right? So I can say, okay, I'm going to take the negative of my most recent answer, right, that 0.841, all right, and then I'm going to add 2 pi. Whoops. So 5.442. All right, so which makes sense because this is 4.71 down here. Over here is 6.28, so obviously pretty close to right in between there. All right, and we're good. These are our 4 solutions. Questions or concerns? All right. So now it's giving us between 0 and 360. So what are we going to have to be careful about here? Okay. So it says graph it, all right, and approximate the maximum point of the graph, then solve the equation, all right? So if this thing is equal to 0, how are we going to solve the equation? What are we going to be looking for? What else do we know is the line y equals 0? The x-axis. Right? Y equals 0 is simply the x-axis. So your x-intercepts, or your zeros, are what's going to be your solutions here as far as your calculator is concerned. Okay. So go ahead and graph that, see what the maximum point is. Do be careful that you need to be in degree mode, that kind of stuff. All right, be mindful of your window. Okay, so again, calculator shouldn't take too terribly long here. So we go into our y equals, right? We can just do sine of x minus cosine of x. So sine of x minus cosine of x. All right, it tells us to look, first of all, we need to be in degree mode. And it says between 0 and 360. So my window, my x min is going to be 0. My x max is going to be 360. All right. Not really sure what the max and min are going to be, so we can just leave it there for the time being. All right, so that easily has our max in there. All right. So here we can just use our second trace feature and go down to maximum. Right, it says left bound, so my cursor needs to be somewhere to the left of that maximum point. All right, hit enter. Right bound, I need to be somewhere to the right of that maximum point. Guess you can just hit enter. All right, so the maximum, did it say the maximum point? Yep, so we need to give it as an xy. So this is just 135, right? You don't need to put 0.00001, right? So that's 135, 1.414. Right, so that's our maximum point. Right, it says then solve. Okay, well, we kind of said since it's equal to 0, that's just the same thing as the x-axis. All right, so if I do second trace now and go to 0, right, there's going to be two of them, right? It crosses the x-axis at two places. So I'm going to have to do them both. I'll do the one to the left first. So it says left bound, so get somewhere to the left. It says right bound, get somewhere to the right. All right, so 45 degrees. All right, and so now left, somewhere to the left of this 0, and somewhere to the right of this 0, and then an extra enter, 225. Right, now also, this should make sense, right? Because whenever you're subtracting two things and they have to equal 0, what must be true about those two things? Yeah, they're equal to each other, right? They have to be, right? They have to be the exact same thing if you subtract them from each other to get 0, right? 5 minus 5 is 0. 10 minus 10 is 0, right? But you can't do like 10 minus 7 and expect it to be 0, right? They have to be exactly the same. So here at 45 degrees, if you look at your unit circle, right, that's where you have square root of 2 over 2, comma, square root of 2 over 2. Well, that they're equal to each other. So if you do square root of 2 over 2 minus the square root of 2 over 2, you're going to get 0. Same thing here at 225 degrees. All right. They're both negative square root of 2 over 2. So since they're the same, since they're equal to each other, that's how we get the 0. Okay. Right. I mean, this isn't really anything that we really need to talk about here. Yeah. Okay. Okay. Find all solutions in the interval. Find all solutions in the interval here, and find. Okay. So this is a good one. All right. So just go ahead and use this equation. All right. And actually find, say, okay, I only care about solutions between 0 and pi over 2, which is in our first quadrant, right? Here, I only care about solutions between 0 and 2 pi, which is our entire unit circle. All right, and then it's just finding the general solution. The general solution is all solutions, where you do like the, plus or minus n times your period type thing. Okay, so go ahead and find the solutions for all three of those cases. And it says explain the similarities and differences. So just kind of think about what's going on. Of course, some of the solutions are obviously going to overlap. Okay. So let's kind of take a look at what's going on here. So obviously, we can just divide both sides by 2, and we get sine of x is equal to 1/2. Right? Well, if we're just doing it on the solutions 0 to pi over 2, well, in the first quadrant, where is sine of x 1/2? All right. Well, that occurs at 30 degrees, or pi over 6 if we're doing it radians, right? So here, x is equal to pi over 6. All right. Now finding all the solutions on the unit circle. All right. Well, x is equal to pi over 6 and 5 pi over 6. All right. And then the general solution, we would have x is equal to pi over 6 plus 2n pi, and x is equal to 5 pi over 6 plus 2n pi. All right, so similarities and differences. Well, I mean, similarities, right? Obviously, pi over 6 is in every single solution set. All right. The similarities in between the first quadrant and the entire unit circle, all right, well, of course, they share pi over 6, but the difference here is this 5 pi over 6, but it's actually very similar to pi over 6 in specific ways, right? Like when we talk about all students take calculus, all right, so sine we know is going to be positive in quadrant 1 and in quadrant 2. All right, what is similar about these two angles? I'll be impressed if anybody gets it.
They're equal distance from the outline, the horizontal line.
They're equal distance from the x-axis, right? And that's very good. there's a special term that we have for those. They have the same reference angle, right? They have the same reference angle. Remember when we talked about finding reference angles? We were like, what's the fastest way to the x-axis, right? Well, these are both the same distance from the x-axis, okay? And that's always going to be kind of the case, right? And then, of course, the general solution is the same as, the 0 to 2 pi solution. We just have to say plus or minus, right, the period to get the infinite solutions. All of the coterminal angles have to be covered here. All right, obviously, this is not your homework. I'll put another assignment up on Delta Math. I haven't done it yet, but I'll put one up that focuses a little bit more with using the calculator today. And I'll go ahead and do that now.